Hello again, everyone. It's Dave Giles here for the next lesson on the Wave unit, sorry, for IGCSE Cambridge International Physics. And today we are looking at the electromagnetic spectrum. So the first thing I want you to do is describe parts of the electromagnetic spectrum and then apply the wave speed equation to the electromagnetic spectrum, with the first learning objective taking up most of the session today. So first of all, we're looking at radio waves. So using radio, television, and slightly more modern, we've got Bluetooth. So short wavelength radio waves carry more information, but over a smaller distance, whereas long wavelength radio waves carry less information, but over a larger distance. So using that information there, out of these short and long wave, which one do you think Bluetooth uses? And the answer is short wavelength, because Bluetooth can be used to transmit quite a lot of data. However, it's only over a small distance. You know yourself from using devices like your phone, connected to your watch or your speakers, etc. You can probably only have it, say, about 10, 20 meters, depending on the terrain, whether it's got to go through walls. Microwaves. Again, you know this one, I'm sure. I'm sure you've all used a microwave to put food, to reheat food. So microwaves penetrate into food. Or just penetrate food. Microwaves are absorbed by water and transfer energy to the water, making the water heat up. It can also be used for communications in mobile phones. And maybe a slightly less well-known use is they also can be used for speed cameras. Now, infrared. So here's some infrared images. The top one is a toaster. And you can see from the scale here, the bluish areas are relatively cold. So if something is given off infrared, it's also given off heat. Again, here, this is a hairdryer. As you'd expect, the handle is the cold bit. And here, where the air is coming out, is the warm bit. This is an ice lolly. So you can see the center of it is very, very cold, as you'd expect. So the hotter an object, the more infrared radiation it gives off, which is used for night imaging. It's used to transmit signals in remote controls as well. And some phones, so this is me about 6 years ago, some phones have got a filter, usually iPhone's got a filter in there, which won't pick up, which will stop it from picking up the infrared. However, most other phones, or most other camera phones, if you hold your remote control, say a television remote control, like I'm holding up here in the corner, to it and press on it, you should be able to see. In fact, I'll try it. Look at the top corner of the screen. I'll adjust my aircon. Sure how well that is showing up. You can't see it too well here. Oh, you can see it, yeah. So ultraviolet next. So ultraviolet is emitted by very hot objects such as the sun. Electric sparks and arc welding also reach temperatures that are high enough to produce UV radiation. So some gases emit UV radiation when electric current is passed through them. Tanning beds and black lights seen in nightclubs use UV rays that have been produced in this way. So one place it's used for is fluorescent clothing. So here's an example of a police officer. Certain chemicals absorb ultraviolet radiation, which our eyes cannot see, and then re-emit it as visible light. These chemicals are also used in safety clothing, as well as some washing powders to make white material appear whiter under sunlight. Some countries also use it in their money. So you can see here, this is an English £5 note. And that five, for example, isn't visible normally. However, you shine it under ultraviolet and you can see it. You can also get ultraviolet pens where you write it on, say, your expensive items like your television. You can write your information. So if it's stolen, you can then shine ultraviolet light on and prove that it was yours. And also used in sunbeds as well for tanning, cause the skin to tan. Tanning beds imitate sunlight by emitting artificially produced UV rays. And X-rays are next on the electromagnetic spectrum. So if you've ever been to hospital with a broken bone, or even if you've been to have a tooth exam, the chances are at the dentist, the chances are you've had an X-ray at some point. And they are part of the electromagnetic spectrum. They are very penetrating. They are found between ultraviolet and gamma rays. So this is some of the order visible light, ultraviolet, X-rays, then gamma rays. So they've got a short wavelength between 0.1 nanometers, now nano is 10 to the minus 9, and 10 nanometers. So very, very, very short wavelength, but relatively high frequency. X-rays are very penetrating and can pass through many forms of matter. They're used in medicine, industry, and security to take pictures of the inside of objects. They can be used for treating cancer and crystallography. So X-rays pass through soft tissue, such as skin and muscle, without being absorbed or without much being absorbed. You might get a slight shadow from it. Denser tissue, such as bone, can absorb X-rays. Film that is exposed appears black, and areas that are not exposed because of X-ray absorption are white. I'll go back to this point a little bit. So when you go for an X-ray, normally you'll put if it's your foot being examined, you'll put it on a table. They will put the X-ray film underneath. The X-ray film doesn't actually contain X-rays, but it can absorb X-rays, and then they'll put an X-ray gun, for want of a better term, just above the area that is being imaged. They will fire X-rays at it. When it gets to your bone, the bone will absorb the X-rays, but the rest of it will not, and then that gives an outline of what your foot looks like, or your bone rather, in your foot. X-rays are used by custom staff to check for weapons and drugs. Badges pass through X-ray machine, which instantly reveals the contents. Even an articulated lorry can be X-rayed. You can see here, looks like some people being smuggled in with this lorry. So X-rays are very useful. They allow doctors to examine the inside of the human body without using surgery. However, X-rays are very dangerous and can have harmful effects on living tissue. So X-rays are very penetrating and pass through flesh without being absorbed. Dense materials such as bone absorb X-rays, which is how X-ray images are formed. Any X-rays that absorb can have severe effects on cells. They are ionizing, which in chemistry you probably know that ionizing means loss or gain of an electron. However, in this sense, we're looking at cells, and ionizing can damage a cell. So if X-rays are absorbed by living tissue, they can ionize molecules in the cell. This can result in abnormal chemical reactions which may kill the cell. If X-rays are absorbed by cell nuclei, they can ionize the DNA molecules. This will either kill the cell or cause DNA mutations, which may lead to the cell becoming cancerous. Due to these risks, X-rays must be used sparingly and safely. Okay. That is why when you go to get an X-ray, the person taking the X-ray will normally leave the room, stand behind a lead wall, and take the image, because an average person getting a few X-rays every year is not going to be too dangerous. However, the person taking the X-rays, if he was or she was getting absorbed by X-rays, 1,000 times a year, that could potentially be very, very dangerous to them. Next on the electromagnetic spectrum are gamma rays, are emitted by certain radioactive materials and have many uses in medicine. Gamma rays are the thinnest, so the highest energy form of electromagnetic radiation, and are above X-rays in the EM spectrum. They have a tiny wavelength, 0.001 nanometer to 0.1 nanometer, so actually smaller than an atom, which makes them the form of EM radiation with the shortest wavelength. A gamma scan is observed by injecting a radioactive tracer inside somebody. So it'll give off some kind of, it'll give off gamma rays, and you will have a gamma camera outside which can detect the gamma rays, and it'll see where it's coming from. It'll look at various parts of the body. It can also be used for sterilization. Gamma rays are used to sterilize medical equipment because they are highly penetrating and kill all living cells. And radiotherapy is the use of high energy ionizing radiation, such as gamma rays, to kill cancer cells. The radiation dose may come from a radioactive source in a machine outside the body, which directs a beam of radiation at the cancer cells. Healthy cells can also be affected by the radiation applied to the body. And I'd like to mention some of the dangers of EM radiation. Now, pardon me. This is the order of the electromagnetic spectrum, so you need to know the order. You need to know it's radio waves, microwaves, infrared radiation, visible light, ultraviolet, X-rays, then gamma rays. As the wavelength of the EM spectrum changes, the way the different wavelengths interact with matter also changes. As the frequency increases, the wavelength gets smaller. Eventually, the waves are so small that they can interact with the cells, DNA, and atoms. This is called ionizing radiation. So these ones here, up to visible light, are non-ionizing. And these ones here, ultraviolet onwards, are ionized, so potentially causing cancer. Now, normally in an exam, if you're talking about ultraviolet, you always have to mention specifically that it's going to cause skin cancer. So these two will cause cancer. You have to be very specific because it's going to affect the skin. It's going to, because that's the bit it hits on your body. Although visible light is non-ionizing, you should know that it can potentially cause eye damage if you look at something that is too bright. So going back to our previous lessons, we know wave speed is frequency times wavelength, or V equals F lambda, with wave speed measured in meters per second, frequency in hertz, and wavelength in meters. So two very quick equations. Give you a few seconds to do it. You can pause it and then give it a go. So radio wave calculated speed. So you get 3 by 10 to the 8 meters per second. And also the X-ray also travels at 3 by 10 to the 8 meters per second. So what you need to know from this is all electromagnetic radiation travels at the same speed, the speed of light in a vacuum, which is 3 by 10 to the 8 meters per second. So this here is the electromagnetic spectrum in order, going from radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays. You notice as we go this direction, the wavelength gets shorter. So we go from radio to gamma rays, the wavelength gets shorter. However, going in the same direction, the frequency increases. So all EM waves are transverse and travel at the same speed in a vacuum, 3 by 10 to the 8 meters per second. We know speed is wavelength times frequency. So as the frequency increases, the wavelength decreases and vice versa. Also, as the frequency increases, the energy of the waves increase. So here are some questions. I shall give you time to pause it, and then I'll put the answers on. So you can pause this, work your way through, and then check it yourself. Okay, and I'll put the answers on now. A little note on this one here. This is what's called a log scale. Now, you might not have covered logs in maths yet. However, the 1500 should be a lot closer to this end than it is to that end. So that goes from 1000, the next one's 10,000. So obviously it's going to be a lot closer to 1,000 than it is to 10K. The last answer is also on there. Okay, thank you very much, people. 1 second. So the next lesson is on reflection. I'll be uploading that fairly soon. I will also soon post a link in the description to that. So I'd just like to say thank you very much to everyone, and I'll see you for the next lesson. Bye-bye.